AP, this is Mrs. Sargent again. I just wanted to start this video with the answers to the last example on the video for 19.2. I think it might have cut us off before we got to those. So your rate constant is 1.1 times 10 to the negative second, 1 over hour, and your half-life is 63 hours. So I told you that the first order integrated rate law is the most common and the one that is highly tested on the AP exam. I did want to give you guys some examples of the second order integrated rate law and also zero order. So the second order integrated rate law, the differential rate law is rate equals your rate constant K times the concentration of A squared. The second order integrated rate law is this equation. That is 1 over your final concentration minus 1 over your initial concentration is equal to your rate constant times the time. A plot of 1 over your final concentration versus time produces a straight line with a slope of K. This is the only straight line plot that will produce a positive K value for your slope. So that's one easy way to identify that graph. And here is showing the plot of the natural log of a concentration. And if you look at the tangent, you're going to see that you have a negative K. Now, when you plot 1 over the concentration of C4H6, you get a positive slope for K. Half-life for a second order reaction. The equation is your half-life is equal to 1 over your rate constant times your initial concentration. So note that the second order half-life depends on the concentration, where first order only depends on your rate constant. Each successive half-life is double the preceding one, and if the initial concentration is halved, the half-life doubles. So I have a table on the bottom of page 4 that summarizes the different orders of the reaction, zero order, first order, and second order. And so you can see the rate expression, that's your differential rate law. The concentration time relationship is shown here, and that's where we're looking at our integrated rate law equations. And then the half-life, we talked about this to find half-life for first order, it's 0.693 divided by the rate constant. For second order, it's going to be, for half-life, 1 over the rate constant times the initial concentration. And then you can also see what the linear plot is. And the slope of the line for zero order, negative K, first order, negative K, and then second order, this is your only positive slope for your straight line plots. So this first example says a certain reaction has the following general form. A produces BB. At a particular temperature, the initial concentration of A is 2.80 times 10 to the third molar. Concentration versus time data were collected for this reaction, and we have a plot of 1 over the concentration versus the time, and the straight line slope is 3.60 times 10 to the negative second liters over moles times second. So when you're looking at a problem and you're trying to decide what order the reaction is, if it gives you a graph where it tells you what is plotted, when it says 1 over the concentration, if we look here, the linear plot, 1 over the concentration versus T, that is second order. Also, our slope was given to us in a positive value, so another thing that is going to tell you that this is a second order reaction. So the first thing says to determine the rate law, the integrated rate law, and the value of the rate constant for this reaction. So the rate law is going to be rate equals K times the concentration of our reactant, which is A, and since it is second order, that is squared. So this is the differential rate law. The integrated rate law is 1 over the concentration at time t minus 1 over the initial concentration is equal to the rate constant times the time. So the last problem, 40, where you guys just had to do A, the first A was just very similar to this, only it was a first order integrated rate law. And then the rate constant, well, the slope, it tells us that rate constant, and the slope is a positive value, and the rate constant is a positive value, so that is equal to 3.60 times 10 to the negative second liters over moles times seconds. Part B says that we need to calculate the half-life for this reaction. So knowing what the half-life equations are for the different orders is helpful to you. So the half-life for a second order reaction is 1 over the rate constant times the initial concentration. So I'm going to take the rate constant that we determined, which is 3.60 times 10 to the negative second. Plug that in here. And then the initial concentration, which we were given in the problem, is 2.80 times 10 to the negative third molar. And so the time that we are going to be given on this 1 over 1.008 times 10 to the negative fourth 1 over seconds, which then translates into 9,920 seconds. And then part C on this question says how much time is required for the concentration of A to decrease to 7.00 times 10 to the negative fourth molar. So this is where we're going to use our second order integrated rate law equation, the rate constant that we found, and we're going to be solving this for T. So 1 over the final concentration, that's what's given to us here, so that is 7.0 let's just slide this over so I can write it out. 1 over 7.00 times 10 to the negative fourth molar minus 1 over the initial concentration that we get from up here in the problem, 2.80 times 10 to the negative third molar is equal to 3.60 times 10 to the negative second times our time. So we're going to divide by the 3.60 on both sides, and you should find that the time is going to be 29,800 seconds. So that gives you an example of a second order reaction. I will post some homework problems And then our next video, we're going to start looking at reaction mechanisms. Thanks. Have a great day.